Oh, so here's like a hard problem that'll cause all kinds of confusion. Let's see. That's not that hard. You want to do the hard problem or talk about the inner ear? Or do we have time to do both? We have time to do both. Okay, let's do this. Okay, so box mass M on a surface mu k. So you got to know what I mean by a surface mu k. Just use your context. What do you think that means? That means a surface where when the box slides on it, the coefficient of kinetic friction is mu k. Okay, I just didn't want to write all that. Right? Pulled at tension T, so the box on a mass M on a surface mu k is pulled at tension T at theta. Okay? So most problems would not be that the opposite of verbose, right? They'll give you more detail and they'll give you a drawing here. So here is the drawing, mass M mu k and tension T at angle theta. Right? And here's the interesting question, is what angle, or what theta gives the maximum A, the maximum acceleration, right? If I have a constant tension I'm going to pull with, I can take that tension and I can pull this way. And you say, well, that would give you the most force in the right direction, but also has the highest friction. Right? I can say, oh, okay, I'll use my tension to cancel some friction. Oh, now there's hardly any friction, but I'm not really pulling it to the right, am I? It's like my accelerating component is gone. So somewhere in between is the right value. Okay? Somewhere in between is the right value. So let's go through it real quick. Some of the forces in the y equals 0. You're given that it's sliding, right? So let's go through the sum of the forces in the y real quick. In the y, we didn't do a free body diagram. Oh my God. M, G, N, T, like that. And then F, kinetic. There's your free body diagram that includes friction. Okay. Let's see. So in the y, we're going to do it the fast way. We're not going to do all the angles in detail. N is up, minus mg is down, right? And then t, it's the sine component, plus t sine theta equals 0. Basically what we just did, because the friction doesn't act in the vertical direction. So we get the normal force, again, is mg minus t sine theta. The normal force reduces, the tension that we're pulling up with reduces the normal force. Right? So now let's look at some of the forces in the x. This is where it gets exciting. Is mass times acceleration. This is the thing we're trying to mess with. We want to know how we can get the maximum A, right? So we say, okay, in the x we have t cosine theta, pulling it to the right. This has no component in the x, no normal force, no weight, but Fk is pulling back, isn't it? Minus F, the kinetic force. And that equals the mass times the acceleration. Okay, so this is new. Now we're getting pulled by tension with friction. Very exciting, okay? Let's fill this out a little bit. We have t cosine theta minus, but what is the friction, kinetic friction? That's the one that's constant, right? We don't have to think about static and varying. It's just mu k times the normal force. But this is the new normal force. Mg minus t sine theta. Mg minus t sine theta equals ma, right? So this tells us the new normal force. This is your new normal. And this tells you the acceleration. Okay? All right. I check the time. Okay, we're cool. That tells you the acceleration. So, but now let's look at the question. So that's kind of like this typical thing I do in lecture, and I say, okay, you're fine now. But then this impossible question comes along. You have to do by yourself. So the question is, what theta gives you the maximum A? Right? So what value of theta is going to maximize that A there if you plugged in a bunch of the numbers? You could do it in your calculator. You'd probably make a little plot, right? That's what you guys would do. I saw somebody nod. I know. Or they have been falling asleep. I don't know. What you would do in terms of calculus, though, you might remember maximizing a function. We would write A as a function of theta. Can you write this function? A is a function of theta, to go back to your algebra notation there. Well, you can. You just divide through by that mass, right? So then you have A equals t over m cosine theta. That's just a constant times cosine theta. Minus mu k times g, because the m cancels. All right, that's just a constant. And then plus t over m sine theta. And if you want to find the maximum of a function, what do? You set something equal to something, right? You set the derivative equal to 0. Maybe that phrase sounds familiar. Gives you an AP calculus nightmare. So we're going to say, let's calculate dA d theta in this calculus-based physics course. Okay? What's the derivative of cosine? Negative sine. So this becomes negative t over m sine theta. What's the derivative of mu kg with respect to theta? 0, because it's a constant. As you change theta, does this change? No, it's a constant. Plus a constant, plus 0. The derivative of sine is cosine, plus t over m cosine theta. And to find the maximum of a function, you take the derivative and you set it equal to 0. Like that. Why do I not have a mu anywhere? Oh, I don't need a mu anywhere. Hold on. I dropped a mu, didn't I? Yes, let's see, that mu was supposed to distribute. There we go, mu k. Thanks for having my back. There's supposed to be a mu right there. Okay. And therefore, there's a mu right here. There we go. Okay, so we set it equal to 0, and now we just start canceling things, right? If we set these, it's just these two terms are equal. The tension cancels, the mass cancels, and we have sine theta. It goes to the other side. It makes it positive, equals mu k cosine theta. Well, that's starting to sound familiar. It's basically saying that the tangent of theta is mu k. Okay. So the angle, I'll call it max, theta max. As soon as we set it equal to 0, we were finding a specific angle, theta max, not just any angle. Max, right? So theta max is mu k. So if we want the angle that gives us the maximum acceleration, it's the inverse tangent of mu k. Okay. That's what you need to know. So you'd say, well, the kinetic friction, it's like 0.5. So take the inverse tangent of that, and that's the angle that'll get me the most acceleration. It'll make it move the fastest. Now you might say, well, that almost looks exactly like when we tilted the ramp to measure mu s, doesn't it? It was inverse tangent of mu s. Is this like the same? It's like, no, it's totally just, it's coincidence. They have nothing to do with each other. Right? For the other one, the frictional force was varying as we changed the angle. Here, the friction force is constant. It's totally different equations. It just happens to come out the same. Okay? You might also say, if you're a smarty pants, you might say, how do you know that was a maxima? It could have been a minima. I'll take another derivative and blah, 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 blah. I also happen to know from a close personal friend that if you add sine and cosine, it kind of looks like that. So that original, the first extrema that you see will be a maxima. But it could have been a minima, and then we'd have been screwed. But I wouldn't let that happen. Okay. And then if we wanted to plot this, inverse tangent looks something like this. If we wanted to say, okay, for all the mu k's we could have, what theta max is it going to look like? And it kind of looks like that. So sure enough, the higher mu k, the bigger the friction force, the higher the angle you need to pull, right? Because the bigger the friction force, the more the benefit is to overcome the friction force. Friction force is small, you're better off just pulling like this. Friction force is big, you want to pull like that to get the maximum acceleration. Right? So that's kind of that's an example of a tricky one, just with one part instead of like 5 parts. Okay.